Hi and welcome to the Impact Hub. I'm not sure, a couple of you walked in as if you know the place. Who of you has been here before? Who of you knows the Impact Hub? Okay, wow, that's quite a few already. Well, welcome to all of you. It's great to have you here tonight. My name is Cornelia and I am from the Impact Hub. I've no idea what you're going to talk about tonight. I had to literally spell the things out because it's all Chinese to me. I'm very much in awe of you. First of all, about the Impact Hub, we are part of a worldwide network of co-working spaces, and all the people that work here are very positive people. We try to create something good, something nice for the future. Everyone thinks about sustainability or about how to make a positive impact, and it's a great movement, and it's great because we all support each other. We have a lot of connections, we have a lot of networking, and we have a lot of events, most of which are, by the way, open for everybody. So please do check out the homepage munich.impacthub.net. For example, this Saturday we've got a free party with swapping things for charity. Amazing. Please all feel welcome. And last but not least, I've got a couple of announcements. First of all, the bathrooms are, if you walk around that screen, down the corridor and to your right. Hard to miss. The emergency exit is right through here, and the second one is the normal main entrance that you came in. Another emergency exit is straight down here, straight on, not turning right to the bathrooms. That's another emergency. The Wi-Fi password is on, you can see that on the walls, and people who are sitting on the stairs will find it on a couple of sheets of paper in between them. And that's all from my side, and have a lovely evening. Welcome to that.
Jetzt darf ich auch was Nettes sagen. Als erstes möchte ich mich bei euch allen bedanken, dass ihr heute erschienen seid, denn ohne euch würde sowas auch nicht stattfinden. Und ich möchte mich natürlich bei Datastax für die Zusammenarbeit bedanken, bei unserem Speaker Claus Samuelsen und Patrick McFadden. Ja, und dann möchte ich euch noch sagen, dass wir ein Gewinnspiel für euch vorbereitet haben. Das ist dieser Zettel hier. Und zwar, wenn sich mehr als 30 Leute anmelden, vergeben wir eine IntelliJ JetBrains License. Genau, also füllt es schön aus, Vorname, Nachname, E-Mail und der Rest. Und dann möchte ich euch noch sagen, dass am 2. Dezember auf dem zweiten Zettelchen, da findet ein Meetup in der Lightweight Java User Group statt. Und zwar kommt da unser Kollege zum Beispiel, der redet über die MongoDB und Docker. Da gibt es einen Talk drüber und noch 2 weitere Talks. Hinten befindet sich noch ein weiterer Talk in der Hadoop User Group. Ich muss euch leider Bescheid geben, dass der doch nicht, also der findet nicht am 9. Dezember statt. Wir geben euch aber Bescheid, wann es doch noch stattfindet. Okay? Hat jemand Fragen an mich? Oder war alles klar? Super. Also ich glaube, keiner hat Fragen. Dann fangen wir mit Claus Samuelsen an. Bitte schön.
I know there's a couple of people standing up. There's more chairs over there, so if we need, we can put up a couple of chairs more. Well, I never think. Thank you. It's really nice to see so many people for an event like this. My name is Claus Samuelsen, and I work for IBM in Europe. I work with big data full time and have been doing that for almost 4 years now. So in IBM, I'm considered experienced big data Hadoop person. And yeah, I'm not going to talk about Hadoop as such and all the facilities that we have in Hadoop. And I'm going to mention the IBM distribution of Hadoop, which is called Big Insights, a couple of times, but I'm not going to speak very much about it. It's about being able to access data in the Hadoop system using SQL. That is what it's about tonight. So, a brief introduction to Hadoop, and then why do we want to use SQL in Hadoop? And then a little bit about what is going on in the Sql landscape in Hadoop. And then Big SQL 3, which is IBM's SQL implementation in Hadoop. And don't be afraid to ask questions. I won't bite or hit you or beat you or anything. Und ich spreche ein bisschen Deutsch, aber heute ich will English sprechen. Ja. So, how many of you are using Hadoop today? About 10%. How many of you knows what Hadoop is? Oh, that's more than half. Perfect. That's really good. So, Hadoop is you can call it an ecosystem of a lot of modules. So Hadoop there's the Hadoop core system, then there's the distributed file system, there's the MapReduce technique for processing data in parallel, there's Hive, which is an SQL method of accessing data, there's HBase, which is a NoSQL database, Scoop for moving data from relational databases into the Hadoop system, Uzi, and I can continue with a number of different modules that are in Hadoop. But the main thing in Hadoop is the distributed file system, HDFS. That's the piece that connects all the nodes in the cluster together. That's the piece of software that makes it possible to process the data in parallel. So that's the big thing in Hadoop. So just a few words on the Hadoop distributed file system. So what is a distributed file system? Means that all the nodes in a cluster can see the same data. And when we load data into the Hadoop system, it is automatically spread out on all the data nodes in the cluster. We are using a way of moving the data around that is called splits. So if you have a huge file, like 1 terabyte or just a couple of gigabytes, then the file is split up into smaller chunks of either 64 or 128 megabytes. And in this way, one file is distributed physically across the cluster, and that makes it possible to process each piece of such a big file on each data node in parallel. Whenever you are loading data into the Hadoop cluster, data files are replicated a number of times, typically 3 times, and that is to make it the Hadoop system high, to have a high availability in the system. Using this method, one node can crash and you can continue processing because you still have 2 other copies of the same data available on other nodes in the cluster. So when we are processing data, we are processing data locally on the data nodes. We don't want to move data from one data node to another data node. The typical setup for disk systems in a Hadoop system is that you have what is called JBOD, just a bunch of disks that are physically local on each data node. So when you are running a job in the Hadoop cluster, you are determining where are the data located on which nodes, and then you are sending out processes to these nodes, and you will process the data there. So you don't need to move them from one data node to another data node. That gives good performance. Okay, SQL. Why do we want to use SQL in the Hadoop system? Because in Hadoop from scratch we are programming in Java. And Java is not SQL. But the problem is that if you ask people, IT people, what skills do you have? Probably more than 90% will say, I know SQL. Then 50% will say, I know Java. 30% will say, I know C++. 1% would say, I know Pascal or something like that. But the amount of knowledge about SQL is really, really huge. So if you're able to use those skills in the Hadoop system, then you can very fast get up to start. That's one reason for using SQL. Another reason is that in the Hadoop system, we can manage all kinds of data. We can manage sound or video. We can manage all kinds of text, but we can also manage what is called structured data. That is the kind of data that we have been putting into relational databases for the last 35 or 40 years. We call it structured data, but it's also a kind of simple data. Small integers and decimals, dates, and if we're talking about text, we're talking about very short text strings like first name, last name, product name, or whatever. So there are a number of reasons to use SQL, especially because even though we can handle all kinds of data in the Hadoop system, a lot of the data that we're putting into the Hadoop system is structured data. And structured data is very easy to manage and to analyze with SQL. So if we look at the SQL landscape, I think I will shut down my phone. No disturbance. Fly mode. Hive is a part of the Apache open source software stack, and it came into Hadoop quite early, like 5 years ago or more. And it brings the SQL interface to the data in the Hadoop file system. Then there has been a number of different approaches to implement SQL in Hadoop. So here's a number of them: Teradata, Asta, Hawk, Impala from Cloudera is quite a lot up in the time as well. So all of these, they have different strengths and weaknesses. The biggest weakness is probably that most of them are not standard SQL. It's only a small subset of the SQL. So it's difficult to use standard tools for accessing the data. There's also a number of limitations in the Sql language that are supported, a number of limitations in the data types that we typically use in SQL. Then IBM has created a new SQL engine to the Hadoop system, and this is called Big SQL, and that is what I'm going to talk about quite a lot today. So Hive was the first implementation. It's a kind of de facto standard for SQL in Hadoop. And all Hadoop distributions that you find will include Hive. One good thing, but also at the same time a bad thing, is that when you're using Hive, you are executing MapReduce jobs. And sometimes it's really good to do MapReduce jobs, but other times it's not so good. MapReduce has quite a large overhead. So if you're just doing a small query on a small part of your data, then the MapReduce has such a huge overhead that it's taking much longer time than if you were using other means. But anyway, if you look at the data when it's stored in Hive, it is just files. So Hive has a concept of using a directory hierarchy. Usually it's called Hive, warehouse, and then the name of the tables, or eventually a schema name. And then just a bunch of files. And it is just simply files. So you can access the files not only with SQL, but you can also access the content with any other tool that is available on the Hadoop system, if it is able to read files. The files can be of many different kinds. So it can be pure text files, flat files. It can be sequence files. It can be Avro files. It can be packet files, and a couple of more file types. So it doesn't. An important thing is that if you are using a relational database for your SQL data, you start by putting a schema. You start by designing how you want your data represented. And then you create the tables, and then you load into the data into these tables. In Hive, you're just having a file in the file system, and then you put a schema onto the file without changing the format of the data. And then by using this schema, you can access the data with SQL. That's a very nice thing to do because it gives you a huge amount of flexibility. Sometimes you want to work on the data using SQL. Other times you might want to use just reading the file using Java, for instance, and doing some calculations that way. So that's probably one of the biggest advantages of an implementation like Hive.
Question.
Yes?
These file 1 and file 2, is it somehow guaranteed that they are sitting on the same data node?
I have to have this question again.
This file 1, file 2 in
Yes.
the directory, are they sitting on the same data node, or are they distributed to different nodes all over the cluster?
So the question is, when you have like this file 1 and file 2, are they guaranteed to be on the same data node, or are they distributed across the cluster where you can have really many data nodes? The answer is, it actually depends. So if it is small files, it's quite likely that they are on the same data node. As long as a file is under 64 megabytes, it is only one piece of a file. It is not split into different chunks. So usually you want to have large files because then you are sure that they are split into a number of chunks, and then they are automatically spread across the cluster. There are a couple of tools you can use to move files around automatically in the cluster. So there's a tool called Rebalancer. So if you have been loading in a number of, let's say that you start up with a cluster with 4 data nodes, then you add 2 more data nodes. Then these 2 data nodes will be empty, there will be no data on them. But then there's this tool called Rebalancer, and you can start that, and it will actually start to move data around, so you get an even distribution of your files on the different nodes. You can also do that if you had loaded in a number of small files, and they all ended up in 1 or 2 data nodes because they are not split up. Then you can also run this rebalancer to move data files around in the cluster. So when we talk about a table, an SQL table in Hive, it's actually metadata that we put on top of the file. We don't touch the content of the file. When we create a table on a file, we just create some metadata saying how this file looks like internally. and then we can start to move, to put SQL on the files. We are using a technique that is called SERDI. SERDI is serialization, deserialization, and that is one of the most fundamental things in the Hadoop system. So there's a very deep functionality that is called formatting, and these formatting functions, they can be used to create new functions that can work on a number of different file types. So if you, I don't know if it is readable, the very lowest lines on the slide, but it actually describes how you can use these SERDI rules to define how you read and write a certain file. So when you store or when you create a table in Hive, then you say create table and create the definitions in standard SQL almost. But then you add some extra information, and the extra information tells you about the file format and what kind of file type it is stored in. So in this example, it says format delimited field terminated by pipe, stored as a text file. So it means that the file that is used for the table is a flat text file, and the fields in the file is delimited by the pipe sign. So it's readable in any editor. You can just access it. And when you create different tables in Hive, then you will end up with a directory hierarchy like this. But one thing that you can do is you can actually do partitioning. And partitioning is a feature that has been in relational databases for quite many years. It's a method for avoiding to read all the data in one file. So if you, in the example here, it says partitioned by state code. And this is probably American state code, so it's like NJ for New Jersey, and AR for Arizona, and NY for New York, and so on. What you gain with doing partitioning is that when you do a query where you say select from blah blah blah, where state equals NJ, for instance, then you only need to read the NJ data. So you can skip maybe 90% of the data in the table. The way it is implemented is that when you are creating a table with partitioning, you will get a directory for each value that you partition on. So here we will end up with, probably if this is American data, we will end up with 50 directories, one for each state in USA. It is. Now, the Hive meter store, that is where we store all the metadata. So when we create a table, all the definitions, when we say create table and defines all the columns and things like that, that is just metadata. These metadata is stored in a traditional relational database in the Hadoop system. Typically, there's an open source relational database that is called Darby. So most Hadoop distributions, they are using Darby. We used to use that in the IBM distribution as well, but we have replaced it with what we consider a much better relational database today. So all these metadata, they contain information about how the structure is about the table, or how you want to interpret the data file. It also contains information about where the data is located on the different data nodes in the Hadoop system. It contains information about partitioning, if you have created tables with partitioning. And it also, and finally, it has information about read permissions, write permissions, and all of these kind of things. So, that is standard Hive. That is what is in all Hadoop distributions. Now I'm going to talk about Big SQL. And it's version 3 because we have already have a couple of versions before this one. And I'm going through why Big SQL is different from the other SQL implementations in Hadoop distributions. A few words about IBM's Hadoop distribution. It is called Big Insights or Big Insights for Hadoop. It is based on all the Hadoop, Apache Hadoop software stack. So we have all the standard modules that comes from Apache. Then on top of this, we don't change anything in the Apache Hadoop modules. But on top of this, we have put a lot of different technologies that we have in IBM. And one of the most important things is that we really want to change the Hadoop system from just being a storage system where you can store a huge amount of data to also be a true analytics system. So we have put in a number of different analytical tools that works on the Hadoop system, so you can do almost any kind of analytics in the Hadoop system. We have also put in a lot of other things like, so it fits into enterprises, so security, authentication, and other things. But I'm not going to go into these details today. Today it's about SQL. Now, when we started to discuss what is it that we want to do with the IBM SQL implementation in Hadoop. So the first thing was that we want to have standard SQL. So you can use, if you have applications today that is running on a relational database like DB2 or Oracle or Microsoft SQL Server or whatever, there's tons of these SQL database systems out there. So if we implement standard SQL compliant technology into the Hadoop system, then it should be possible to migrate or to move your applications from the standard setup to the Hadoop setup. That was one of our goals. We also wanted to support a huge amount of the different kinds of file formats that is being used in the Hadoop system. So if you have a relational database, you typically have something that is called a DB space or a table space, which is a very specific disk area that is used by the relational database. And in this disk space that is allocated to the relational database system, you put in your tables by using pages and other kinds of techniques to get high performance and things like that. In the Hadoop systems, we want to use the files that is used standard in Hadoop. So we are using all the well-known facilities of the distributed file system. Another thing is, that's what in the green square here is performance. We want to have really, really good performance. I already mentioned that MapReduce is good for some kinds of workload. But for a lot of workloads that you typically are doing when you're working with SQL, MapReduce is not very good. It is slow because it has such a high overhead. MapReduce is made for batch processing. It is made for reading all the data in the files that you're working on. It's not made for reading just a small part of the file. So we have implemented a very modern massive parallel programming feature for running SQL in the Hadoop system. We also have optimizers. So when you send SQL statements to the SQL engine in the Hadoop system, the optimizers will look at the SQL and find the best way to execute the statement. So it can actually, sometimes it will rewrite the SQL statement. Because when rewriting an SQL statement, we will get the same result, but we can execute it in a faster way. We also want to be able to have a lot of concurrent users accessing the data at the same time. And we don't want to be constrained by memory limitations. So we have a number of nodes in the Hadoop cluster, and there might be 16 gigabytes or 64 gigabytes of memory in each node. But if you have a huge amount of data and you're running a lot of jobs in parallel, then you can easily use all the memory. So we want to have techniques implemented that if we are working on larger data amounts that can be kept in memory, we want to have techniques that can handle this. That's called spill factors and things like that. Then we want to have what we call enterprise features. Security is in most companies, data security has very high priority. So you have data in your system that some users may see and other users may not see. So we want to have the ability to set up rules for which data a certain user can access. Then we have to have workload management. So we don't want a situation where one heavy job is providing all the users for running their jobs. We also want to have something like self-tuning. So if we put extra load on the SQL engine, then it should automatically be able to reallocate memory or reallocate CPU resources, things like that. And then, of course, monitoring, being able to see what is happening and things like that. And finally, federation. Now that's the lower left square. Federation is the ability to query data in different systems at the same time and joining the data. So if we have data that are in the Hadoop system, then typically we will also have an Oracle database or a Microsoft SQL database or a DB2 or Informix or whatever that is outside the Hadoop system. And these relational databases, they are typically updated daily with a lot of new information. So these are the traditional transactional systems. So many times it is not very efficient or smart to move these data to the Hadoop system because they are updated so frequently. So instead we want to be able to, from the Hadoop system, when we are querying data that are in the Hadoop system, we want to be able to at the same time connect to a remote database and join the database, join the data that are in tables in the remote database and get a result. That is called federation. And today we are supporting DB2, we are supporting Teradata, we are supporting Oracle and Netezza, and I think we have a couple of databases more that we support. And then finally, which is here, the rich SQL, we want to be able to use all the well-known features of SQL that we have known for 20, 30, 40 years in the relational database world. We want to have stored procedures, so we want to have this kind of user extensibility to put new functions into the SQL engine. So that's quite a lot. So still, when implementing all this, we still want to have the flexibility and the freedom that you also have in Hive. So we don't want to put constraints on how data is stored. So we want to be able to use all the different kinds of file types that Hive can use. We also want to have no constraints on how to access the data, because sometimes it is more efficient to write an application in Java instead of doing SQL access to the database or to the data. So there's a number of different kinds here. Pig, for instance, I don't know if any one of you are using Pig Latin, but Pig Latin is widely used programming language in, can you see? In Hadoop. It's a functional programming language, but it is not SQL and it is not Java. It's a high level where you concentrate on the logic and not on the technical implementation of MapReduce. So here's an example of how we create tables in big SQL. It is standard SQL. The only thing is that we put in this special word, create Hadoop table. By saying create Hadoop table, we are telling the SQL engine, now we are creating a table in the Hadoop system. As we have a relational database system in our distribution, you can use create table and then create a table in a traditional relational database. But to be sure that we are working in the Hadoop system, then you put the Hadoop keyword into it. Then, these are things that are not in Hive, but only in IBM Big SQL. So we can put different kinds of constraints on the table definitions. So not null or null, where we are telling if we are allowing data not to be present in the table. It is not enforced when you write data into a file, but it is enforced when you are reading data. So if we have put a not null and data is missing, then you will get a warning when you're running a query. So even that it is not enforced when writing the data into a file or to a table, it has a really good function, because this information is used by the optimizer in the big SQL. So that means that if you put these kinds of information into to the create table definitions, then you are giving the optimizer a number of hints so it can produce better query plans.
I have a question.
Yes?
If you have data structure, data where you are not sure about your data structure, you're just saying, I'm just saving it, maybe I can use it later.
Yeah.
Is it possible when you create the metadata that you can analyze it, that you get help how the data is put together, so you can create something like that?
Yes. So the question was, if you're not sure of what structure you have in your data, what do you do with that? So if you can get the data, you just store the data in the structure that it is created with from wherever it comes from, and you load it into the Hadoop system. Then after that, you can use create table on the file that already exists, so you put metadata on. And you can actually, on the same file, if you want to, you can create different tables. So if you have a piece of information that can be interpreted in different ways, then in one table you would say, this 20 bytes of information is actually 3 different columns, or maybe it should be treated. Hello. Maybe it's, there's a chance over here. Maybe it should be treated as one entity. So you can do anything that you want. You don't need to change how the data is stored in the file. You can just put different kinds of metadata on the same file. Is that the answer to your question?
Yeah, this is answer to my question, but I also was thinking about that maybe a kind of job is analyzing it and getting some kind of structure that maybe can help me in creating the metadata.
Oh yes. Yeah, so the question is when you're analyzing the data, you can actually create new metadata, or you can create results. So I mean, you can do anything you like. So there's no limitation there. I'm not 100% sure that I understand your question correctly, but...
Can I rephrase the question, because I think it's quite interesting.
Sorry?
Can I rephrase the question in my words? I think I understood what you meant, and I think the question is interesting. So, if I understood correctly, the question was more, is there some kind of automatic way to come up with the schema of the files? So you have the files in the Hadoop file system, and you want to tell the database, come up with some kind of metadata which represents my files in a coherent way.
Well, many times there is, so many times you're using CSV files, plain flat CSV files. And if the CSV file has the first record or the first row in the CSV file is header information, then you already knows what the different columns are in your table, because you can take that directly from the CSV file. If you have, for instance, what is called a fixed length field file, so from position 0 to position 6, you have the date. From position 7 to position 16, you have the time. From position 17 to 20, you have some other information. If you have that kind of file, then you have to specify it quite precisely, because you cannot see directly from the file, from the content of the file. And that makes it a bit more difficult. So there's a number of different file formats that has information about the content. For instance, if you are using Avrofiles is specialized for what is called serialization, deserialization. But the very nice thing about Avrofiles is that in the first part of the file, it contains all the metadata about what kind of data you have in the file. So when you're working with Avrofiles, you don't need to have a knowledge about the content. You can simply read the meta information in the start of the file. So that makes it very flexible, and you can use the same file for many different types of operations. Yes?
Extend a bit this question about defining, referring the types of the comments of one type similarly to the same question. Does IBM have some kind of semantic analyzer or something to refer the types?
Yes. Okay, so the question was, does IBM have any tools for analyzing a certain file for what kind of data is in the file and things like that? Yes, we have that kind of tools. It's not part of our Hadoop distribution. It is part of a product called Information Server, and I think it's called Data Analyzer or something like that. And you can process a lot of data with this and get information about data types and content, and also information about if there are in place some records contain wrong information and things like that. So we have that kind of tool, but it's not part of our Hadoop distribution, so you have to buy it as an add-on or extra. Okay? Another kind of constraint is what is called primary key constraint and referential constraints. It is not enforced, so you can, if you have two tables and you define referential constraints, you will not get an error if the values in the two different tables does not fit. But the optimizer in big SQL will use this information for finding the best and most efficient query plan or execution plan when you're running jobs on the tables. Primary key and referential constraints. So I think I've already mentioned, these are the different file types that we support with big SQL. So we support flat files, what is called text delimited files. Usually it's called CSV files, comma separated files, or character separated values. We support sequence files. Sequence files is a binary file in the Hadoop system that is very efficient to read. We support Parquet. Parquet is a key value pair structure. And if you really want high performance, then Parquet is absolutely the best file type to use. Then there's RC and ORC files and Avro files. I've already talked about Avro files. So all these different kinds of files, they have features or advantages and disadvantages. So depending on how you want to use your data, if you're only going to use SQL to access the data, then I would recommend using Parquet because Parquet is really efficient. If you want to use any kind of tool that is available in the Hadoop system for accessing the data, then maybe a flat text file is the best. Maybe it's not so efficient, but it is very, very flexible. You can read it with a simple editor. So you have always no limitations on how to work with these data. Now, the next thing is how do you populate data? So if you already have data files in the Hadoop system and you want to use big SQL on top of the data files that are there, then you can say create external table. Create external Hadoop table. And by using the external Hadoop parameters, then you are saying that I'm defining table metadata on an existing data, on an existing file. And you will not, you don't need to move the file, it can be placed anywhere in the Hadoop cluster. And then you tell what format the file is. So here it is row format, delimited fields terminated by comma. Store as a text file, and then location. So you tell where the file is located in the Hadoop file system. The typical way to get data into a table in the Hadoop system is by using a load command. But in big SQL, you can also use insert. But I would not recommend you to use insert except for testing or something like that. Because every time you execute an insert sentence, you will create a new file in the directory hierarchy. So this line here, where it says insert into table T1, values 5 and 6 and 7, that inserts 3 records or 3 rows. So it actually creates one new file for this sentence. if you set insert into and then just values 5 and then a new insert into values 6 and so on, then you will get a huge number of files. And Hadoop is not meant for a lot of small files. There's a number of different constraints in having a huge amount of files. So we have something, when we are using HDFS, the Hadoop Distributed File System, we have something that is called a name node. The name node contains all the metadata about the files in the Hadoop system. So where they are located, what kind of files and names and directories and so on. And all this information is kept in memory on the name node. So if you make 1 billion small files, then you have to have a lot of memory in the name node.
Sorry to interrupt.
Yes?
I don't want to be rude, but how much longer are you going to do it?
Sorry?
How much longer are you going to
Oh, about 2 hours.
2 hours? You're all going to stay for 2 hours?
No, it's, I know I've already talked about almost 1 hour, so
okay.
I will or just make 2 or 5 minutes. Is that okay?
That's fine.
Okay.
That's fine. No problem.
So I will probably skip a couple of slides from here. Yes, so we have a load Hadoop, which is very efficient for putting data into. And with the load Hadoop, you can use a URL, so you can actually get data from servers that are outside the Hadoop cluster. So you can directly load data into a table with this command. You can also connect to a relational database and simply retrieve all the information from tables in the relational database. Just requires that you have a JDBC connection to Oracle or DB2 or whatever you're using. Yes. So, a bit about the SQL language. So it's a full SQL 2011 SQL implementation. So you have all the facilities that SQL has. So you can, I don't know, this is probably not readable from distance, but it's a very complex query with subqueries and using things like exist and not exist and so on. There's a huge amount of statistical function in big SQL, so you can really do a lot of analytics that you usually do in your data warehouse. You can do that as well in the Hadoop system. Architecture performance. So this is how the architecture looks like. Big SQL engine is running on the same nodes as MapReduce jobs are running, but we are using another scheduler for running the SQL jobs. But it's on the same nodes as MapReduce is running. So, not much more about that. Yeah, resource performance.
Someone has a question.
Yes.
Right here.
No, we are not using MapReduce. We are using our own massive parallel programming technique. So we have big SQL agents on each data node. So an SQL job is distributed to all the nodes that has the data when you're querying the data. It's very similar to MapReduce, but it's much, much faster than using MapReduce. Oh, yes. So this is a benchmark. This is the time it takes to run a certain query. And this is a number of different queries in a TBC benchmark. which is called TPC-H benchmark. And the yellow columns, they are with Hive, and this is the number of seconds or milliseconds it takes to run the query. And the blue columns is the big SQL time it takes to run the same query. So you can see here, and on average, on this benchmark here, big SQL was 41 times faster than Hive.
This is all read performance.
This is
all read operation.
It's only read operation. The question was, is it only read or is it also write operations? No, it is only read operations. This is another TPC benchmark that is called TPC-DS. It is much bigger. It has 99 different queries. And you can see the pattern is almost the same. Big SQL is much faster than Hive. Yes?
Can you say anything about the performance between big SQL and Hive 0.30 with 10?
Yes. So Hortonworks, which is really doing a lot of the development with the Hive and using a component called TES, they have been saying that using Hive 0.13 is much faster than Hive 0.12. We have tested, we have not published these figures yet, but we have tested with Hive 0.13, and it is faster, but it doesn't come close to big SQL, not at all. Unofficially, I was doing a POC in Italy a couple of months ago, and the customer was testing with Hortonworks, with Hive and TES. The customer was also testing with Cloudera, with Impala, and then with IBM and Big Insights with Big SQL. Impala was 10 times faster than Hive, 10 times faster than Hortonworks. But Big SQL was 3 times faster than Impala. So even Impala is really fast, but Big SQL is much faster than Impala. I think I will stop with this. I have a few more slides, and my last slide is a number of links to IBM sites where you can download our software, where you can find a lot of information and so on. I will provide this presentation as a PDF file, and then some of those who is arranging this event tonight will get this file, and you can distribute, put it up on meetups or send it out to whoever wants it.
Okay, great.
And that's my small speech tonight.